In this video, I want to look at another example of a problem where it's particularly useful to convert to an orthonormal basis. So in the past, you'll remember that when we talked about projecting onto a subspace, we said that the projection of some vector x onto, we'll call it a subspace V, was equal to A times A transpose A inverse A transpose times the vector x. So we had this super weird looking formula, and we said at that time that this formula was actually going to simplify depending on the basis that we used, and this is where that comes into play. If, for example, we use an orthonormal basis specifically to define V instead of some non-orthonormal basis, then as it turns out, this value here in the center, this A transpose A inverse, that whole thing actually simplifies to just the identity matrix. So we end up with A times the identity matrix times A transpose and times the vector x. But of course, as you know, multiplying by the identity matrix is like multiplying by 1, just in matrix form. It doesn't change the value of anything. So then this formula actually simplifies to just A transpose times the vector x, which tells us that if we want to project the vector x onto some subspace V, then all we need is the matrix of column vectors that define V and its transpose, and if we multiply them together, then we'll have a projection matrix that we can multiply by any vector x that we want to project onto V. So this is yet another example of how using an orthonormal basis instead of some non-orthonormal basis can drastically simplify our calculations and our formulas. And this is actually a really important part of linear algebra. Being able to pick the right basis, to pick a basis that's going to make your calculations easier, is going to be really important. And so that's why we're looking at different examples of how an orthonormal basis simplifies different kinds of problems. So to see an example of what this looks like, let's actually use the vector set from the previous video. Remember though that in the previous video, we had a vector set with 3 vectors, v1, v2, and v3. Because they were orthonormal to each other, and we had 3 vectors all in R3, each of these vectors is defined in R3, we know that together they span all of R3 space. Well, for the purposes of a projection, it's not really going to be very interesting for us to have a vector set that spans all of R3, because then if we want to find the projection of some vector in R3 onto the subspace, if the subspace defines all of R3, then the projection of x into all of R3 is just going to be x itself. It's not going to be some other projection vector. It'll just be x. So we eliminated v3 so that we just have 2 vectors. These 2 vectors together define a 2-dimensional plane inside R3, which means that now we'll have some interesting results. When we pick any x that we want to, we can project it onto that plane, and we'll actually get a projection that isn't just x itself, the x that we picked. So we've already verified that this set is orthonormal. Remember, to verify that the set is orthonormal, we just need to make sure that each vector dotted with every other vector is 0. And we know that if we take the dot product of v1 and v2, we'll get 0 because we have 0 times this value, 0 times this value, and then 0 times this value. So the product of each of the components will be zeroed out, so that dot product will be 0. And we need to verify that the length of each vector is 1. And we can see here that the length of this vector is 1, and if we take the length of v2, we'll end up with 1/2 plus 1/2, and we'll get a length of 1. And again, we did that in the last video, so we've already seen that this set is orthonormal. Of course, keep in mind that if you have some orthonormal set like we did in the last video where we had v1, v2, v3, if you take away one of the vectors from that set, or multiple of the vectors from that set, the remaining set is still going to be orthonormal, because like we showed in the last video, these 2 vectors are already orthogonal to each other and they have a length of 1. Taking away that 3rd vector doesn't change the fact that these vectors are still orthogonal to each other and still have a length of 1. So if you have a vector set with 10 vectors and it's orthonormal, you could take away 2 of them or 5 of them or 3 of them, and the remaining set would still be orthonormal. So we know this is an orthonormal set, and what we're saying is that this set forms the basis for the subspace V, which means that we can define A as the matrix of these column vectors. So 0, 0, 1, and then 1 over root 2, 1 over root 2, and 0. So that'll be the matrix A that defines the subspace V. And then, of course, according to our formula here, we're also going to need A transpose. So A transpose will then just be, we'll get 0, 1 over root 2, 0, 1 over root 2, and 1, 0. So then with A and A transpose in place, we can go ahead and find the projection matrix, which is the product of these two. So we'll say A transpose is equal to, and we'll multiply these together. So 0, 0, 1, 1 over root 2, 1 over root 2, and 0, multiplied by the transpose 0, 0, 1, and then 1 over root 2, 1 over root 2, and 0. So now when we multiply these together, we'll end up with a 3 by 3 matrix. So we'll get here 0, and then 1 over root 2 times 1 over root 2 is 1/2. So we'll end up with 1/2 there. The first row times the second column will be 0 plus 1/2. The first row times the third column will be 0 plus 0. Then the second row times the first column is 0 plus 1/2. The second row times the second column, the second row times the third column, and then the third row times the first column, we get 0 plus 0. The third row times the second column, 0 plus 0, and the third row times the third column, we get 1 plus 0. And so when we simplify here, we'll end up with our 3 by 3 projection matrix, which will be 1/2, 1/2, 0, and then 1/2, 1/2, 0, and finally 0, 0, 1. So this will be our projection matrix, and we can now multiply it by any vector x that we want to in order to find the projection of x onto the subspace V, which is defined by this orthonormal set. So let's say, for example, that we want to find the projection of the vector x, which is just 1, 2, 3. We want to know what the projection of this vector is onto this subspace V, where this subspace is a plane defined by these two vectors. Well, we simply multiply this projection matrix by this vector, 1, 2, 3. So let's go ahead and put that in there. We'll say by 1, 2, 3. And so when we find that projection, we'll end up with here a vector in R3, of course, starting with the first row times the column. So 1/2 times 1 is 1/2. 1/2 times 2 is 2/2. And then 0 times 3 is 0. And then taking the second row multiplied by the column, we'll get 1/2, 2/2, and 0. And then multiplying the third row by the column, we'll get 0, 0, and 3. So we'll simplify, and the result then is 3/2, 3/2, and 3. And this then is the projection of this vector x onto V. So we can call this the projection of the vector x, where x is 1, 2, 3, onto the subspace V, where V is defined by this orthonormal set. It's a plane in R2. So that's why it's so advantageous to use an orthonormal basis to define the subspace instead of some non-orthonormal basis. The projection formula simplifies drastically for the projection onto a subspace, and we're just able to find those A transpose matrices, and then simplify down to a final projection matrix that we can multiply by any vector x that we want to project onto the subspace.